So yeah, I'm gonna talk about the long-awaited massive model grids for binary C. So yeah, Rob has been telling you about a grid. It's actually several grids, hence the S here. So what we want to do is basically cover the mass range from zero point 0.1 solar masses to 1,000 solar masses. Cover an extensive range of Z. This is going to be slightly trickier, I think. I'll come back to this later. Have grids for the actually 16 evolutionary steps in early 2002, and maybe later introduced through rotation, magnetic fields, well, extra physics. So when I say cover the mass range for this mass range, basically we want to have access to the supermassive stars that have been suggested as drivers for cluster mechanics by Mark Gillis, also Corinne Charbonnet. To have access to POP3 stars, so those very young, very low metallicity stars. Nina has been harassing me with them this week, so proof this workshop is working. Well, the problem so far is that MESA ZAMS models, well, actually PMS models, go from 0.08 to 100 solar masses. You can cheat a bit by pushing it to higher masses and let it relax, but I don't think you could push that a bit higher by a factor 10. So probably something has to be done to feed MESA some kind of PMS structure or very early main sequence structure for those stars and then relax them. Cover an extensive range of Z. Again, it's for POP3 stars. The problem here will come from the MESA opacity tables. I've not dug into it at all, so I don't know. Maybe if Warwick or something or someone like that is on. They know more than me on this for sure.
Before you continue, can I ask about the MESA ZAMS models? So, what is exactly the issue? Why can't you go beyond 100 solar masses?
Well, MESA has a bank of pre-main sequence models that you interpolate and relax when you want to have access to a given model with a given metallicity.
But you can create your own zero H-main sequence with MESA. So MESA would anyhow not come from a pre-main sequence model like a polytrope to go to a 100 solar mass star, but it would rather take a, say, 30 solar mass star, evolve it from the pre-main sequence to the zero H-main sequence, and then just accrete mass onto this object until you have reached whatever mass you want to have.
Yes, that's the part. That's the tricky bit I mentioned here. Do you really think you can accrete like 900 solar masses on top of a?
Why not?
Sure, why not? I mean, just take a zero H-main sequence star of whatever 30 or 50 or 100 solar masses that you already got, disable all the nuclear evolution, and just simply accrete mass until you are at whatever value you want to be.
I can definitely do that in the stars code.
Yeah, so that's also not a problem, I think, in MESA.
Yeah, okay.
It simply doesn't ship predefined zero H-main sequence models for such high masses, but you would just have to create your own file. I think there's really no bigger problem in principle, at least.
Okay.
Yeah, that's the key. In principle, there isn't.
Yeah, I've been stuck with a lot of things that were in principle easy so far. So maybe I'm shit. Maybe it's slightly more tricky than expected. Both theories are, I think, equivalent in probability at this point.
I think you also care about physics a bit too much, perhaps, because how you define the zero H-main sequence of 1,000 solar mass stars, I'm not sure anybody really knows what that means.
Yeah.
So it's...
Yeah. I'm getting to this slightly later. Let me just write down what Fabian just said. Okay, so what we want to do is to cover the 16 evolutionary steps that have been highlighted by early 2002. Those are the ones used in binary C already. Here they are. I'm not going to get through those, but basically you have normal stars, helium stars, compact objects. Well, the thing is, we want to have a grid for each of these stages, and they have to be rectangular. There's a huge speed loss coming. A huge price to pay if your grid is not rectangular is that you have to change your interpolation routine, and it becomes super slow. So you want to cover all masses equally with the same number of points along each evolutionary step, and that is going to be quite tricky. One thing I want to highlight is that in BSC, the age is the main variable to trace quantities. You use mass to compute things in the fitting formula they provide, but age is still the thing you use. And when you have mass loss or mass gain, you basically convert the age in that given stage using the rule of 3. So in the main sequence, for instance, you have here prime shows, well, the quantities with the prime are for the new star that has lost or gained mass, while the non-primed quantities are for the previous one. And well, basically, if you gain mass, your star is going to have a slightly shorter main sequence lifetime. So you just use this rule of 3 here to convert the age of the star before to the new one, and you evolve from that. The second one here on the right is the same thing for the Hertzsprung gap. So Hertzsprung gap goes from what they call TMS, that is the terminal age on the main sequence, to the base of the giant branch. And you just use a rule of 3s in that range. And it goes on for other other stages of the evolution. So my plan is to have 16 different grids for these stages. It's gonna be modular. I'm going to mention this a bit at the end. And the grids need to be built differently compared to what we have at to what Hurley fundamentally does. So what I want to do is disjoin these steps, have well set boundaries where you have starting conditions, typically ZAMs, with a coherent definition of the ZAMs, endpoints, just like the TAMs, and a nice definition for that too, and use some kind of proxy for the age, an indicator of evolution that works for that phase. For instance, along the main sequence, naturally you would go for the core abundance of hydrogen. It's not that obvious for other later stages. And then obviously, if you want to build the grid, you need a nice definition of what is satisfactory to save, like how converged you want your models to be and such. And also, obviously, to build the grid, you need to know what you want to print. So a clear list of the outputs we need to basically cover everything that BSC is already computing and potentially introduce new physics. So I'm going to go through each evolutionary stage now and show you a bit what we have decided to do. The first one is the massless remnant, done. So now the main sequence. For the main sequence, the boundaries are clearly the ZAMs and the TAMs. So the ZAMs, there are several definitions. You could go for something like, you know that the PMS stars contract and then they start expanding slowly on the main sequence. So when you have this dr over dt equals 0, that's where your main sequence starts. That's the definition. It's not often used, but it exists. You could have some criterion on the contribution of hydrogen fusion to the total luminosity. Could be 90%, 99%, something like that. I have read something very weird in the MESA mailing list about time step things, where basically your pre-main sequence finishes with a small time step, and then on the main sequence, because that's easy to compute from MESA, the time step goes up dramatically, and you could spot that increase in the time step. Well, I don't like it at all because I care a bit too much about the physics, and I don't feel like there's anything physical in that. And then the last idea, that is the most interesting one, comes from Aaron Daughter via the MESA user mailing list. Basically, you evolve your star through the pure main sequence. You start the main sequence, and when you have started burning some helium, some hydrogen into helium, you spot that, and you backtrack to the point where your luminosity first reached some significant contribution to the total luminosity. That's probably what I'm going to try and do. It's not super easy to implement, but it's not really hard either. For the TAMs, the definition is much clearer. It's basically when you have exhausted hydrogen in the core, you can't really use MESA's built-in tools to spot zero abundance of hydrogen, because you don't have any satisfactory definition of the relative error to that, and also because your hydrogen is never exactly zero. So far I've been using 10 to the minus 5 as my core hydrogen exhaustion limit, but this could change. The proxy for age, as I said, is obviously the core hydrogen abundance. How to spot a satisfactory model? Well, everything is built in, so you can actually specify some chemical species that you want to track in the star, and then spot when the central abundance of that species reaches some value. So in this case, for instance, you would spot automatically when your star gets to 0.2 in central hydrogen abundance. And these two, when to stop R-tol and A-tol, are tolerances on that value. The formula is not super, well, I didn't put it, it's not straightforward, but who cares?
Can I ask a question about how you get to that in MESA? It's a MESA.
Oh, that's a block that you have to put in your enlist file.
Sure, but then does it move forward in time until it overshoots, then start back again and with a half time?
Well, yes, exactly.
Okay.
You basically retry the time step, so that you divide the time step and
that's fine.
The quantities that are required that we identified with Rob are obviously the mass, radius, luminosity, age. These are not over time, but over core abundance. Also the derivative of the core abundance. The time derivatives of the radius and luminosity are also useful. I forgot to put them here. E2, that is some term in the equation that allows you to compute the synchronization timescale. I took the formula from Rob's work, even if that's not Rob's name, and lambda from Zahn 1989, which is also related to tides.
So Mathieu has a question regarding core masses.
I didn't say it.
He says we should also record core masses, but the problem is that there's no really easy way to define a core mass on the main sequence. There's not a very well-defined core, except in the case where you have a convection zone in the core. So we can record the convection zone mass.
Yeah.
And radius. That's quite easy.
For low mass stars, your radiative zone is basically much larger than the actual core where you fuse stuff.
Yeah.
And yeah, actually Hurley in both papers, they define main sequence stars as having no core.
That's right. So the question is, what would the core be useful for on the main sequence? Maybe Mathieu.
Beyond MS. Well, I'm getting there. Don't worry.
Yeah, we'll get there. We'll get there.
Well, just a small thing. I was not able to retrieve the plot, but the plots Rob showed me. But we implemented a preliminary version of that main sequence grid. Rob ran it and it worked. So this is promising, I guess. After the main sequence comes the ominous, often overlooked Hertzsprung gap. So basically subgiants. The boundaries of that step are not too hard to define either. The start is the terminal H main sequence, and the end is the base of the red giant branch. So how do you define the base of the red giant branch? Probably as the hydrogen ignition in a shell. And here, there's this question I have that it's mostly for Rob. Do we need to save some structure info at that point about that shell burning hydrogen?
What do you mean?
Well, is there something that we would need about the structure that is useful for binary C?
Core mass, core radius?
Core being the part inside.
Where the shell is.
Okay. Yes. Okay.
Gio, can I interrupt once more?
Feel free to interrupt anyone.
Moments of inertia as well.
For the base of the RGB, I don't think that you can use a hydrogen ignition of core also, right? I mean, in the massive star, and also in the lower mass, and then in the lower mass stars, hydrogen burning just moves from the core into a shell, and then this continues essentially for the whole evolution. So there's already off-center hydrogen burning before you reach the base of the RGB. And the same is true for massive stars. Yeah, so if they end their main sequence lifetime, they do this little hook, and at the end of the hook, they ignite hydrogen in a shell. What is probably a better definition is that on the RGB, you are almost fully convective, or you have a really large convective envelope, and maybe something like this could help, because you're essentially on the Hayashi track. Or, of course, you go immediately up to core helium ignition.
Yeah.
For the proxy, while I'm at it, I found it sometimes quite useful for any interpolation purposes to define path length in the Hertzsprung-Russell diagram.
To define what?
Use a path length in the Hertzsprung-Russell diagram, essentially delta log T effective plus delta log luminosity square, and take the square root of the whole thing. And you could add, for example, also the surface gravity or something like this, and this would give you a quantity that changes rapidly with the evolution, and so you can map this actually quite nicely into H. So it works even on the main sequence. It would work across the Hertzsprung-Russell diagram. It will probably not work once you are in a position in the Hertzsprung-Russell diagram where the star does a lot of things in the interior, but the surface doesn't change anymore.
So the issue with that, I don't think it would work in binaries when you have mass transfer, and you want your interpolation variable to be something to do with the evolution of the star. And if you're starting to just use, say, convection zone mass, that doesn't really tell you very much about the evolutionary status of the star.
Yeah, but even if you do the binary evolution with binary C, you're always relying simply on single star tracks. I mean, you would also there use the age of a single star, regardless of...
We're doing it differently.
Yeah, the point of the grids here is to avoid the age as the variable you use for the interpolation. That's what I mean by proxy for age. It's basically we're okay with using a different variable for this interpolation at every evolutionary stage, but we don't want to have the age as that variable, because when you rejuvenate the star, suddenly, when you transfer mass, you have some kind of rejuvenation, not as extreme as the one you showed, but anyway, that kind of makes the age irrelevant.
I know, totally agreed, but I think what you're only looking for is a way to interpolate in the data or in the table of single stars and to find a variable that is better than the age, right?
Well, the problem I have with the path length you suggested is that you basically need, if you use something that is like the core mass evolving monotonically and quite easily, something that's quite easily accessible like that, you can basically, how to say that? I will be saving the start and the end boundaries before filling in the grid. So when you compute the path length, it obviously depends on the path your star follows. So you need to know the whole evolutionary track to compute it and sort of integrate over that evolutionary track. When you use the core mass, you just need to know the end result.
Yeah, but also what I'm thinking of is that you replace, or you come up with a variable, call it, I don't know, interpolation variable, and you feed it with whatever information. And the only thing that this interpolation variable tells you is between your points of interest, for example, now, say the end of the terminal edge, or at the terminal edge main sequence and the beginning of the RGB phase, to have a quantity that allows you to put the star somewhere in this range, and this quantity that you use to put the star in this range does not need to have any physical meaning. The way I understand it is that this is only for interpolation in the tables of these single stars, and then you want to use them in binary C.
The problem then is, though, that if you say merge two of those type of stars, where do you put your star?
Sure, that's going to be difficult, but this is also going to be difficult if you use the core pressure for the proxy for the age.
Oh, sure, I agree. But if you
this is not going to go away, this problem, or core mass, or whatever. You will have to come up with a way.
Core mass is relatively straightforward. You merge two red giants, you add their cores. That's pretty easy. So some physical variables are easier than others to add in that sense.
Mm-hmm. Yep, absolutely
And
right.
that's kind of why we want to stick to things that are sort of physical rather than things that are constructed.
No, but what I want to say is, if you have a proxy that doesn't depend on physics, so you could then still use this proxy to come up with, okay, what is now the age of these two stars that you're merging, and then you use the old Hurley prescriptions to know what the next age is that you want to find, and then you can go back from the age again to your proxy variable, and then you have the model that you're looking into. So this proxy variable is really just a smart transformation, if you like, that allows you to interpolate in these tables in a sort of effortless way.
So the good thing is that on the main sequence, you can just use core hydrogen abundance. That's fine. On the giant branch, the core mass works very well as well. The only time you need this is in the sort of things like the Hertzsprung gap, where it's a bit more messy. I don't know what that proxy would be on the Hertzsprung gap.
Yeah, that's why I listed. So I don't really know either. That's why I put.
Yeah, I mean, the thing that changes in the Hertzsprung gap quite a lot is, for example, the temperature.
Sure. Oh, temperature would also do the job to some extent. Question is it the best thing to use when you want to, when you have, I don't know, like mergers, to take the extreme case, and you want to.
Or on the Hertzsprung gap, a lot of them make algol-like systems, so
If
you
you
lose
have
a lot of mass.
Transfer, which one of these variables that evolve monotonically on the Hertzsprung gap, which one do you want to use? Which one is the most convenient to retrieve for this new system, this new star that has lost or gained mass?
Well, even if you have, I mean, you could even just use age, in fact, because you have these points of interest where you know that your star is a Hertzsprung gap star. And so you know that you have to look into your grid of Hertzsprung gap stars, and within this grid, even age just continues in a normal fashion. Well, not then on million years time scales or whatsoever, but just on thermal time scales of the star, right? So even that would be possible.
Yeah, that's kind of what we do now. We have a start and an end, and we interpolate linearly. So I'm not sure that's right.
Yeah, I don't think age is good here, because if you have a star that starts the Hertzsprung gap, suddenly inflates, it drops a lot of mass on the companion, the core will not be changed. So your star is kind of still sort of the same age, core-wise, but has a smaller mass. So you would give it more lifetime. I'm not sure this is the thing you want to do. That's physically irrelevant here. I don't know. Am I making sense?
Yeah, that makes sense to me. I think it's not an easy question to answer. And if we can come up with something based on physical attributes that determine the evolution of the star, like the core mass or the core abundance, then I'd like to do that. The problem on the Hertzsprung gap is that's not what's determining the time in the Hertzsprung gap.
Yeah, but so maybe I misunderstood you. So are you going to make grids then also of Hertzsprung gap stars, and you, for example, you're going to remove the mass just to see what the kind of, no, because you're going to interpolate still in single star models.
Yeah.
Yeah. So then this whole proxy for the age is just really relabeling of the age axis, isn't it?
It's changing the age axis with a thing that is physically meaningful. The feeling we have is that if you were to, for instance, merge two stars with different core abundances, you would build a core that is sort of the mass of these two previous cores, that has an abundance that is sort of the average of the weighted average of the abundances you had before. And this makes more physical sense than saying, okay, this star here, once we have this core with this averaged abundance, we take the single star model we have that fits that. And we feel that it is more physical than merging two stars with two different ages or relative ages on the main sequence, computing the average of, the new age with the formula I showed, and take a single star that has that age.
Okay, so I think I slowly understand where you what you're trying to do. So you say, for example, you want to use some merger prescription that allows you to infer what the core properties are, and then you look in your single star grid. What is that single star that has the closest kind of, for example, core mass, and then you're going to continue with that star.
Yeah, that's what we want to do, and basically we want to define closest in terms of something physical rather than the age.
Okay, so but that's going to be really tough.
We're tough guys.
Yeah. It's more difficult than the old way of doing it, because the old way of doing it involved just making tracks. But are you going to talk about the giant branch?
Yes.
Okay. So maybe we should discuss the giant branch first. Then you'll get more of an idea.
Yep. Just go.
Or have comments about on the chat.
Oh.
I'll show them.
We can do that from here.
Warwick. You can't hear him.
Fabian's.
I'm gradually learning.
That end correspond. Yes, you're right, Warwick. Fabian already alluded to that. I'll look a bit more into this and try to indeed define it better. I've written that down. Have a look. Okay, so you'll be surprised, but the red giant branch is actually the next slide. So the boundaries of the red giant branch goes from the base to the tip. That took me several years of work to figure out. So basically, how do you define the tip of the red giant branch is now the next question. So you take the helium ignition in the core as a criterion for that. That's probably, well, that's actually the definition of the clump, but, well, do you end your red giant branch grid at the beginning of the clump stars? Do you take the maximum luminosity as the exact tip of the red giant branch in the Sprung-Russell diagram? Again, that's the thing I have to define. I'm not sure of the implications of these two different definitions, basically. The proxy for age can be the core mass, the relative core mass, age burning shell radius, so the core radius. All of these work. So far, we've decided for the core mass, well, actually for this MC over M, and core over M. Just like the Ashburn gap, finding the satisfactory model is probably going to take more than using the pre-built MESA controls that are available and require a routine that spots when we are, well, when, I don't know, L changes, derivative or something like that. The quantities that are required along the red giant branch, you have the mass, the radius, the luminosity, the core radius and mass, and the core degeneracy fraction. This is a problem we have here that we need to take into account. Degeneracy in the core. Low mass stars are degenerate in the core on the red giant branch. Higher mass stars are not. So that will play some role in the interpolation. We also want binding energies for obvious reasons that these stars are supposed to be in binary systems at some point. That's it for the red giant branch.
So the only other thing I'd comment on here,
yes,
my original idea was to have a grid that is essentially a square, a rectangle.
yes.
There's mass on one axis, core mass on the other axis. Well, core mass divided by mass, so it's between 0 and 1.
Oh, yeah.
And you can construct an equilibrium model for all of that. You can disable helium ignition, so just turn off helium burning, and you could have it for all of these. Then you can calculate where helium ignites later, and that's part of the evolution algorithm. But,
yes.
And then you could fill the whole thing, and then you can do all of the off-grid stars with no issue at all. They wouldn't be stars that, say, sit on a normal stellar evolution track. So let's say you have a red giant, you're going up the giant branch and you absorb a 1 solar mass companion. Right? So you're a 2 solar mass star with a half solar mass core, you absorb a companion. Then you are then on a track which doesn't exist in single star tracks. But if you have a grid which fills this mass and core mass divided by mass space, it is on that grid.
Yes.
And so you can just change your evolutionary track to there and restart it. And on each of those points, you know what the rate of change of the core is, because you know how fast the core is growing by hydrogen shell burning. So you can just continue your evolution. All you have to do then is work out when helium starts to ignite.
Yes.
And then you have to switch to a core helium burning. Well, but that's fine. You can do that as well. We could even calculate the helium luminosity in the stars in Mesa, but not allow any helium abundance change. Then you would know exactly when helium ignites from this grid.
Yeah.
And I think that should work. I don't see why that wouldn't work. And it's very physical as well. So you can easily do mergers with a companion main sequence, at least to get an equilibrium structure. It's a bit of work because you've got to do all these models over this grid, but that's okay. We have the CPU. The problem's going to be when you're at the top end of the grid, where your core mass is nearly your total mass, and you're
Yes.
almost a proper helium star. You'll have issues with numerics.
Yeah, and also this may take forever to compute. We may be dead by the
Well-
end of this grid.
No, I don't think that's true. Why would that be?
It's moving very slowly up there, but
Oh yeah, sure. We can make some. We can chop the grid at 0.95 or something to make sure we don't get up. That's okay. But it would be really good to get those models with thin envelopes working because they are relevant for the transition to becoming a white dwarf. So for post-GB, post-AGB stars, those are crucial because you want to be able to map the temperature and luminosity from your envelope mass on top of your white dwarf. It gives you timescales across there as well. So that's also very important. We will have to ignore things like shell flashes if they exist out there. It might. Sometimes. With very thin shells, sometimes you get instabilities. But
that would already be a step forward.
yeah, it's a huge step forward. Absolutely. I mean, it means we don't have to do all the dodgy formula extrapolation we did before. It solves a lot of problems with the transition to white dwarfs, planetary nebula formation, stuff like that. It's all automatically in there. So that's why it's a very powerful idea. But it's not easy, as you said. It's a lot of computation.
Okay, so for the red giant branch, that's it. Then, well, these 3 steps.
Quantities.
What? Yes.
Convective envelope mass, and you'll still need the and radius. You need both because you need those for the tides.
Yeah.
The radius, well, that's probably most of the stuff, but that's okay. But the tidal parameters as well.
Oh yeah.
And the lander binding energy.
Yes, that's what I meant by binding
Oh, okay.
energy.
Sure. Yeah. It's my fault.
Okay. Okay. So these are the 3 steps I spent most time thinking about. So I'm gonna go real fast for the rest. 4, 5, 6. Those are still standard single evolution tracks for core helium burning AGB, thermally pulsing AGB. Well, here I'm not sure. Should I make a grid for each element burning phase? Like a grid for helium burning stars, then a grid for carbon burning stars, and then all the way to iron, well, to silicon burning stars. I'm not really sure. Also, it's going to be tricky to manage the various end-of-life events, like planetary nebulae or supernovae or whatever happens there. I don't really know where we'll be able to, how far we'll be able to go with MESA and where we'll have to cut the evolution and call it a day.
So Warwick might have an idea a bit more about, or Fabian, about how far Mesa can go. As far as I know, it can go all the way to silicon burning. So as far as I know, that's true.
What I know for sure is that I have no clue for the proxy for the age or the new interpolation variable, which is actually a better way of putting it.
How does BSE do it?
Gio here, well, if you want to hear my ideas about where you, up to which point you need to go to,
Yeah.
Depending, of course, on what you want to predict, but in terms of the stellar structure changes, really, if you want to know for the radius of a star, temperature, luminosity, and so on, after core carbon burning, they are not going to change. After core carbon burning, you're essentially dominated by neutrino losses, and from that point on, the whole evolution up to core collapse is just instantaneously.
Okay.
Unless, of course, you're interested in the core properties. But if you really want to get all the MESA models up to core collapse, this is a major effort in computing time. And this is where you really spend, I don't know, maybe up to core collapse, carbon core burning, you can use maybe, I don't know, 1,000 models or so, and then you're there. But if you then want to go to core collapse, this is probably another 10,000 models or so. And I'm not sure whether you're going to gain so much in terms of the stuff that you can do then with binary C.
Okay.
So
Okay.
I think I would agree with that. And the issue here is also that we're replacing the existing algorithm, which goes up to the end of helium burning or carbon ignition, essentially. So
sorry, restart this sentence.
So
I was reading my
BSE
message.
goes up to carbon ignition, and then we assume everything after that is very fast.
Okay. That makes
And I
sense.
think first step will replace that, and that's fine for now. Otherwise,
Oh yeah, and there's of course another thing. If you want to compute through core helium burning and then into the later phases, you will encounter AGB stars in the lower mass, in the other mass ranges, and going through, say, all these thermal pulses and whatever with MESA, and this is not going to work out. So I would highly recommend against doing any of this kind of computation. So you probably better.
Sorry, you want to avoid the thermally pulsing phase?
No, I would go and look for models that have been computed through this range already, but not try to recompute them with MESA yourself.
Oh yeah, we can do that to start with. That's fine. But,
Okay.
So take something else for the AGB phase, but try not to compute through this with MESA. I think you're just going to get so many headaches. And
the other thing we could do on the AGB is what they did in the original BSE models, which is to just impose a very long time step so you don't actually have any thermal pulses. And that gives you roughly the correct hydrogen luminosity, hence the luminosity of the star. It doesn't give you the internal physics, so for example, the amount of dredge up and things like that. But that's so dependent on the numerics and on the fine tuning of the mixing that I'm not sure we could really say much about that in detail anyway. Not with any certainty. I mean, at the moment we have that in binary C, but there's free parameters you can tweak for that. So and they really are free. So we can calibrate them to observations, but that's about all. So we could try that. I don't know if anyone's tried to do that with the thermally pulsing phase in MESA. I don't know if it's possible, but we could give it a go.
no idea. I mean, you just have to avoid to see all the helium, thin helium shell.
That's right.
The helium shell flashes in the thin shells. I mean, that's something that you need to avoid numerically. Whew. No idea. I've never tried.
Eggleton's code, but of course Eggleton's code is it's a different mesh, so it's probably a bit easier to follow it. But I don't know in MESA. But we haven't got anywhere near there yet, so that's. And the good thing is the massive stars all explode before then anyway. So.
Yeah. I mean, are we only interested in 1,000 mass stars?
No,
stars because I could do that much faster than. Okay.
I'm hoping to get a PhD student to work on the AGB stuff next year, but that's in the future.
Okay, so yeah, as I said, this is more food for thought than something I really have designed already.
Why can't we use central helium abundance, just like we did with central hydrogen?
Well, for the AGB.
For core helium burning.
Yeah, well, that would work. But then you have the next steps where you have to find a new thing to monitor, probably the central. If you have core burning of some element, then you just have to follow that. But
Yeah.
the transitions are going to be just like the Hirschsprung gap, but worse.
The good thing is that the end of core helium burning ends essentially on the giant branch as you transition to the early AGB, which is pretty quick. And then it just behaves very similarly to a normal red giant. Because the helium luminosity is pretty negligible.
Yes.
So you might be able to just use the normal giant branch grid. Or a variation on the theme that has a chunk of the core made of carbon. That might be, oh, sorry, helium, not burning to carbon. That might be possible. So the way they do it in BSE is they use the same core mass luminosity relation for their AGB as they do for normal red giants.
Okay.
That works pretty well. So we might be able to do the same.
Okay. Why not? I'm also not aware of anyone having. There's a message from Warwick where he tells us.
Has he broken his microphone?
I don't know. He doesn't have. He's not aware of anyone having done that thing you.
Oh, I see.
described. Well, okay, you can read.
True lurker.
Okay, so that was for the end of the giant stuffs. What's next? Oh, the helium main sequence. I put this one apart because even if I'm not one, well, obviously those would not be core burning helium stars. They would be naked helium stars. So you have an helium core that starts evolving by itself once its envelope has been stripped away. It's by for many reasons similar to the helium to the hydrogen main sequence. You simply change the elements in the core. To start, well, I'm not sure because these things don't create spontaneously. You need these stripping even to happen. So where to start computing the grid is not obvious. Obviously, the end is going to be when you reach the core helium exhaustion, and here it should be 10 to the -5. It's not obviously 5. Proxy for age, well, you have the core helium abundance, and you can use the exact same block of stuff for the enlist as you were using for hydrogen, but this time you replace with helium. I put helium-4 only. I don't know if the other isotopes matter. Quantity is required the same as the main sequence, the real main sequence, except that I changed H into HE. That seems pretty straightforward. I'm still expecting to be surprised at some point, but so far, so good.
Have you tried making some of these?
Not yet.
Okay.
And then 8 plus all the rest. So those are the helium subgiants, giants, compact objects. So for the helium evolve stages, hopefully it's going to be similar to the hydrogen subgiants and giants. I'm not really sure what to expect for core degeneracy at all. It's going to be a tricky thing for our red giants, the hydrogen ones. I don't know. What's going to be the impact of a hydrogen envelope on top, if there's some hydrogen left or not?
Can't we just switch back to the red giant? The red giant grid, because that's essentially what they are. It should be continuous across the two. Kinda.
Well, kinda. If we,
the good thing is
it
that
should be similar and at the same time not really, because you're gonna have a helium burning shell without a hydrogen burning shell. So that's gonna be some pretty weird red giant.
Yeah, it's gonna be
but again, maybe we can use the same kind of laws.
The good thing is it doesn't matter so much because these stars tend to have winds which blow off the surface layers. So it's very unusual to get hydrogen accreting on a evolved helium star.
Well, in this case, I'm okay with that.
So I don't think it's such a problem. Really. Even in low mass stars, they have quite strong winds.
Then for white dwarfs, at the moment, I don't know much about them, to be honest. Surface, well, yeah, of course. The discussion this morning is the one that involved Alex, who's sleeping now, and Arman. Well, surface temperature could be a proxy for age. In the end, they just cool over time. Maybe the total energy they have inside, something like that.
So we have a couple of options in binary C for the cooling tracks. Depends a lot on the microphysics at the surface, so which I'm not an expert on, I should say. We have a couple of options for that. It might be good to redo that. I don't know how Mesa does it. Does anyone out there know about Mesa and white dwarfs? I guess people have done stuff, but quite what, I'm not sure.
Did you invite those people who did stuff?
They're white dwarfs. They just sit there and they blow up. Forgot about it.
Well, anyway, if no one here or in the chat or in the conversation can help here, yeah, Warwick, what about the white dwarfs? You're right. That's exactly the question. So I don't know much, but we can probably surround ourselves with people that will help. For neutron stars, again, I'm not sure what MESA can do for them. I don't know if there's much to do with them, to be honest. And black holes, well, everything is defined by mass. We probably just need the Schwarzschild radius. Well, so far nothing is rotating for this first version of the grid.
Yeah.
So, yeah, and the charge too. So far nothing's rotating. So non-rotating uncharged black holes are entirely defined by their mass. So I'm not sure they require a grid. We just have to compute the Schwarzschild radius. Okay, thank you, Mathieu.
Well, we can just steal the stuff for neutron stars and black holes from the US.
I'll come back to this. Well, as I have put here, I have not put a lot of thought in these phases yet. To wrap this up, this is my last slide. So I will compute these grids with MESA, but what I've heard a lot is, yeah, but with MESA, no one really knows what's happening. The PI is not even an astronomer, you know. The accent, it may remove some of the anonymity of this statement, but it was from an anonymous user, non-user.
Sure.
So people that are not happy with me using MESA could still contribute their own code. So apparently, Holy Priest is interested in contributing stars models. I have discussed this with Maurizio Sararis, and he's interested in, well, he would be okay to give us some BASTI stuff. Also, you could use phase-specific models. For instance, there's this Stalin code in Montreal, the PI being Pierre Brassard. They do kind of split evolution to have, in their case, SDB stars and white dwarfs modeled their way. So that could also be included. You don't have to do the whole track with only one stellar evolution code. More information from Mathieu. Yeah, I'll move a bit to the left. I'll put that here because we don't need that corner anymore. Okay, I'll have a look at the papers, I guess. Do you know any of this works, Rob?
Yes.
You do?
Yeah. David does very well.
Okay.
Okay. But we'll have to see a format, so it should be fine.
Okay. Let me write that down. Anyway, to finish, one thing I forgot to put on this slide, but that we alluded to, is that we can also replace only specific phases and keep what was in BSC for the others. Whatever we're stuck with, we can actually revert to the current version or use different models. Also, we want to, one important thing to incite people to contribute their models will be to define a standard format for the grids. Maybe a maximum size. We at some point discussed with Rob the possibility of loading the whole grid in the cache. That would really help with the speed. Now we have to think, well, we have to check it's doable in terms of size of the thing. Include rotation. So should we include rotation using the MESA treatment of rotation? Another one improve MESA to include that other treatment so that we can use it and still use MESA. Well, that's also a thing. And finally, that's my last comment. Can I sneak some seismology into this? That's still to be seen. And I think that's my last slide. It was. Thank you. Thank you for the comments and contributions more than anything.
Do we have any more questions, comments before we go on?
Well, I have questions in general about just the massive of free stars. So apparently you can just keep adding to 100 solar masses until you get the mass that you want.
Mm-hmm.
But then won't the physics be very different just because if you have a pop free, it has by definition zero metallicity. So whatever.
Well, the zero metallicity is going to be a problem. Well, I think it's going to be a problem because MESA has a range of metallicities it can cover, basically for equation of state and opacity tables. And if you want to go outside of that, I don't think you can. Adding mass that has the same properties as the mass that you already have in your PMS model is a thing you can do. And then you can relax to a structure that hopefully looks like what a massive star looks like. But you can't remove metals. So I'm not sure.
Yeah, because that's basically what I would require to use binary scene part of what I'm doing.
I don't know what the minimum metallicity in MESA is. If you guys know how low we can go.
It's the kind of thing Warwick would know, isn't it, Warwick? 0, there you go.
So you can go the way.
I don't see why not. I mean,
my bad.
I don't see why not.
Oh, then there you go.
Okay, so basically you can get a model for
Thanks, Warwick.
technically a zero metallicity star with very high masses.
Sure. I don't see why not. I mean,
I would have expected some shenanigans.
I don't see any good physical reason why you can't do it. It is, as they say, a matter of getting the tables there. But the tables are there. So
okay, thank you, Warwick. Oh well, there's a big message right before that. So Mathieu said, "Oh, you have a question. Sorry, we indeed missed it. Is the plan to move towards a grid of models, removing completely any analytic fit and relying on interpolation?" Yes. The aim is to remove the analytical fits altogether. Yeah. The problem is as you mentioned, in exploring things that you can't get from models, is that sometimes you stray into non-physical territory, and you end up, computing for instance, for very massive stars, you end up using early laws for masses that were not intended to, that were not in the original fits, and what you get is significantly different from what you should have solving the cell structure equations. So based on this problem, we kind of want to push the logic and avoid any of these kind of issues. Yeah, sure. Your last statement is right. If you know what you're doing, you can do whatever you know you're doing.
The good thing is that if you want, you could always construct an analytic fit from the grids that we're making. It shouldn't be too hard to do.
It's even a thing we could provide.
Yeah, we could. That's not too hard to do. And it would be a lot easier than running all the models again, so that should be relatively simple. Do we have any other questions? Anyone at the back? Tom, do you know? No?
I do have a question. So I know that the group of Gallimopelli uses their code 7, and they have updated tables computed by Parsec. Do you know anything about this?
I know about the Parsec code, yeah.
Is this the one you have a lot of experience with?
Well, yeah. I would not make the same comments I've already made in a workshop, but
We can pause the recording.
I was supposed to modify it during my first postdoc, and I was really not happy with the way it was coded, and poor coding was clearly introducing some errors in the code. Now, I don't know if those errors are significant or if they led to anything that may be seen in the results. I don't think so. At some point, I know they were really interested in going to model AGB and TP-AGB stars. So that's the thing they've done with their code that I trust
Is that Marigo and
more. I think the paper is, well, it's Padua people, so Paola Marigo and others, and also Alessandro Bressan in Trieste. Yeah, Bressan is the PI of the Parsec code, but he's not put himself as the first author of papers for a long while. So that paper on TP-HGB stars is probably not his paper, but it's quite high in the author list. It may be Xiaodong Fu who wrote that paper.